So once you have done this, okay, you have constructed a correlation function, then we can check for crossing symmetry and modular invariance. Now, if we pass these tests, this implies that we have a good CFT. But a good CFT does not necessarily mean that we have a good string theory, but not necessarily a good string theory, because it could have the same problems that the bosonic string theory had, for example. Okay. So you have to then check for various other consistencies. So check for the absence of tachyons. Then absence of vacuum instability and so on. Okay, and here you can just basically use the QFT techniques to analyze all these questions. Okay. And after doing that, what one finds, okay, so the result that one finds is that you have only two consistent string theory. In D equal to 10. Of course, you can compactify, okay, wrap up the extra dimensions onto small spaces. Okay. But in 10 dimensions, you have two consistent string theories. Okay. And these are the type 2 and type 2b string theory that we described. Now, yesterday I introduced the Ramon sector, but I didn't discuss very much how to calculate the correlation function in the Ramon sector. Let me just do that right now. Okay. So correlation functions in the Ramon sector can, in principle, be found using the bosonization rules. Okay, so let me remind you that we got these S alphas as e to the I by 2 and then plus minus phi 1 to plus minus phi 5. Okay, so the chiral ones had even number of minus signs, antichiral ones had odd number of minus signs. Okay. So using this representation, we can in principle calculate the correlation functions of S alpha. Okay. But doing that, it's a little hard because you have to keep track of the signs, etc. carefully. Okay. So in practice, we can just specify a few OP, okay, which you can compute from first principle, and then everything else can be derived from those OPs. Okay, so in practice, they can be computed by a few OPs, which I'll write down. Few operator product expansion, and then, of course, analyticity. So what are these operator product expansion? So let me write these down. And as I said, these can be derived using these bosonization rules, but we'll just think of them as given. Okay. Now, if you remember the GSO projection rules, you see that this is GSO even, okay, but this is GSO odd. Okay, you have a signal psi mu. Okay, so you expect the product to be GSO odd, and indeed this is GSO odd because this is anti-chiral spinor instead of chiral spinor. Then you have okay again here. This is GSO odd, this is GSO odd, but this is GSO even. And then you have the product of two of the spin fields. This fixes the normalization of the spin field. This last one, in fact, you can derive from the others, but let me write it down anyway. This is useful. And similar for anti-holomorphic. Plus the corresponding OP is in the anti-holomorphic sector. And the point is that once you use this and use the fact that this is holomorphic, these are analytic in W, okay, del W bar of this is 0, okay, then you can essentially derive all other correlation functions from here. Okay, are there questions? Okay, I'll explain what these gamma mu's are. I'll describe them. Okay, but are there any questions about these operator expansions? Okay, so let me just say what the gamma mu's are. Okay, so these gamma mu's, these are 16 by 16 gamma matrices, symmetric matrices. This is anti-commutator. Okay, so this is the identity matrix. Okay, this is probably familiar. Okay, these are 10-dimensional gamma matrices. Okay. The only subtle point that you have to remember is that in the product of two gamma matrices, of two gamma mu's, upper index, upper spinor index is contracted with lower spinor index. Okay. So, for example, when you talk about gamma mu, gamma nu, alpha, beta, okay, this actually stands for gamma mu, alpha, gamma, gamma nu, gamma beta. Okay, so the upper index and lower indices are contracted. And I'll leave as an exercise based on all these identities is to check that e to the minus 5 by 2 S alpha and e to the minus 3 pi by 2 S alpha. These are both GSO even. These have conformal weights. Zero, 1. Since we have given the energy momentum tensor in terms of psi mu, and we have the operator expansion of psi mu at S alpha, you can easily work this out and check what the conformal weights are. Okay. So this is the underlying conformal field theory. Okay. But now, while trying to construct a string theory, okay, we have to put restrictions on the states, because as we had seen, not every state in the conformal field theory need to be states in the string theory, even off shell. Okay. So let me now say what is a general off shell state in string theory. So off shell state so these are GSO even states. V in the CFT, which satisfy several conditions. First is what we have already seen in the bosonic string theory, that L naught minus on V okay, and let me remind you, L naught plus minus is L0 plus minus L0 bar. B0 plus minus is B0 plus minus B0 bar. So this was the only constant we have in bosonic string theory, okay, for off shell states. Okay. But here we'll put more constants, okay, and that's the constant on the picture number. So an off shell string state will have picture number -1 in the NS sector and -0.5 in R sector. And this should hold both in holomorphic and anti-holomorphic sector. So this is a general off shell state. Now I describe physical state or on shell state. So it satisfies all these conditions, but furthermore it is BRST invariant. Okay, so this is again the same as in the case of bosonic string theory. Okay. And as in the case of bosonic string theory, we have an equivalence relation. Okay. That means that V and V tilde are equivalent if V tilde minus V is given by QB lambda. So for some lambda that satisfies the same condition, B0 minus 1 lambda equal to 0, L0 minus 1 lambda equal to 0. Okay. These condition on the picture number, you don't have to specify separately, because if V tilde and V satisfy the right picture number condition, then so does lambda, because QB has no picture number. Okay, so the picture number of lambda is automatically satisfied once V tilde and V satisfy the correct picture number condition. So what I'm going to describe now are some examples of physical states. So here is an example. Okay, NS sector. These are an exercise. Check that the following state is physical. So to check this, you have to first make sure that it has the correct picture number. It does, because it's -1, -1. Okay. You have to make sure that it has the correct, it satisfies the L0 minus and B0 minus equal to 0 conditions, okay, which again you can check. Okay. And then you have to check that the QB annihilates this. Okay. And that actually puts some additional constraint on xi, zeta and k. Okay. And the constants are that k square should be 0. Okay. And that k mu, zeta mu nu, equal to 0, equal to k nu, zeta mu nu. Okay, so this is an exercise that you can try to do. Okay, I have given the expression for QB, so you have to check that QB actually annihilates this state.
Ashok,
Yes.
do you also put a constraint on the total Gauss number of the physical state?
Well, you can, but in this case, you don't need to. At least at a generic momentum, you don't need to. Okay. But otherwise, you can put a constant on total Gauss number 2. Maybe I can write this down. In the bosonic string theory, we did it. Okay, here also you can do that. But it's not essential, at least not in a generic momentum. You can put total Gauss number 2. Sorry, this is part of the physical state condition, not off-shell string state. So here I can put total Gauss number 2. Okay, which of course this state does have. Okay, so now, and okay, this one you can identify as the graviton dilaton two form fields. Okay, so this is in exact analogy with the bosonic string case. Okay, we have the symmetric part, symmetric traceless part gives a graviton, the trace part gives a dilaton, and the antisymmetric part gives a two form field. Okay, and just like in the case of bosonic string theory, there is an equivalence relation which gives the gauge transformation laws. Okay, you can check that here also we have similar equivalence relation that tells us that certain these zeta mu nu has to be identified. Okay, so zeta mu nu is equivalent to zeta mu nu plus k mu xi nu plus k nu xi mu with k dot psi equal to 0. Okay, this you can interpret as gauge transformation. Right, this is xi bar. K dot psi equal to 0 and k dot psi equal to 0. Okay. The second exercise I'll give you is to check the absence of tachyons. Okay. For example, in the case of bosonic string theory, we had this state, okay, C bar e to the I k dot x of 0 on the vacuum. Okay. This one is not there, is not present. Since it has picture number 00. Okay, whereas the string state should have picture number -1 in the Nebu-Schwarz sector. Okay, so that's why this is not present. Okay. But you have to work a little carefully and check that all the low-lying states, okay, by shifting through all the low-lying states, you will find that none of them are tachyonic. Okay, now let's construct a state in the NSR sector, a physical state in the NSR sector. Okay, so this means it's Nebu-Schwarz on the anti-holomorphic side and the Ramon on the holomorphic side. Okay. And here it is. This has the correct picture number. You can see the picture number -12 and -1. It has a correct Gauss number. It satisfies GSO because this is GSO even. Okay. And it would be -5 bar psi bar mu is GSO even. Okay. And then we have to check the QB, the VRSC condition. Okay. And that gives condition on K and Xi. Okay. So in particular, we have K square equal to 0. Okay. And then you have K mu Xi alpha mu equal to 0. Okay. And then K nu gamma nu alpha beta Xi mu beta equal to 0. So this I'll leave as an exercise. Okay. So this comes from QB V equal to 0 condition. Okay. So this one, if you examine carefully, you see that it has a vector index and the scalar index. Okay. By examining the spectrum carefully, one finds that this has a spin 3/2 and spin half state. Okay. So the spin 3/2, massless spin 3/2, you can identify as the gravity no. Okay. This one you can identify, think of as a gauge condition. This you can see, you can interpret this as a some version of the Radhika-Sanger equation in an appropriate gauge. Sorry, I think something is wrong. I think this is not correct. This is new. Yeah. So this you can think of as some version of the Radhika-Sanger equation in this gauge. Okay. So this is gravity no plus the dilatino, okay, which is a super partner of the dilaton. Okay. So that's the interpretation of these states. Okay. In fact, in this case, there is another gravity, no? Another set of massless spin 3/2 plus spin half state. But this time from the RNS sector, where the anti-holomorphic side is Ramon and holomorphic side is Nebu-Schwarz. Okay. And this has the same chirality in 2B because the GSO projection rules are the same into on the two sides in 2B. Okay. And this has the opposite chirality compared to the NSR sector into A. Okay. So this is of course only at the level of the spectrum. Okay. One can also check consistency at the level of the interactions, okay, of, for example, decoupling of pure gauge states and so on. Okay. And at the end, what one finds, okay, is that these theories describe n equal to 2 supersymmetric theories in D equal to 10, okay, which are nothing but type 2B or type 2A supergravity, coupled to an infinite tower of massive states. Well, all string theories have this property that you have an infinite tower of massive states. Okay. But unlike these theories, type 2B and type 2A supergravity in 10 dimensions, okay, these are string theories, and as a result, okay, there are no ultraviolet divergences. Okay, and this is what we achieve, okay, by including these infinite tower of massive states that are implied by string theory. Okay. And the absence of ultraviolet divergence will follow basically the same line of argument as in the case of bosonic strings. Okay. Are there questions? Okay, now let me say a few words about the heterotic string theory. That's also important. Okay. So in the heterotic string theory is a mixture of superstrings and bosonic string, okay, in the sense that the holomorphic sector is like superstring, and the anti-holomorphic sector is like bosonic string. Okay, which basically means that there are no beta bar, gamma bar, okay, or equivalently xi bar, eta bar, phi bar, okay, and there are also no psi bar. But this raises the question as to what about D? Okay, that is the number of X mu's. Because these certainly cannot be 10 and 26 at the same time. Okay. So what one does in this case is that we take 10 X mu's, okay, so X0 to X9, and then we add a CFT of central charge 16,0, so that effectively, if we look at the T bar X plus T bar CFT, okay, this has central charge C bar equal to 26, because 10 comes from the T bar X, and then 16 come from T bar CFT. Okay. And then everything else becomes consistent. So this is essentially what underlies the construction of the heterotic string theory. Are there questions? Now it turns out that CFTs of central charge 16, 0, these are holomorphic or anti-holomorphic CFTs, okay, are quite rare, quite restrictive. And in effect, we only have two CFTs consistent with crossing symmetry and modular invariance. Let me remind you, crossing symmetry is the symmetry of the 4-point function, and modular invariance is the symmetry of the torus 1-point function. Okay, and once these are satisfied, then you have a consistent CFT. Okay. So these two CFTs give rise to what is called E8 cross E8 heterotic and SO32 heterotic theory. Now these names, okay, I'll explain what these names come from. Okay. They essentially come from the fact that the CFTs, both the CFT have dimension 1,0 currents. Okay, these are operators. Okay, currents by definition, dimension 1,0 or dimension 0,1 operators are called currents. Satisfying the following relation. Okay, where these are the structure constants of either E8 cross E8 or SO32. Okay. Both of these have 496 generators. Okay. So the number of J bar are the same, okay, but their operator expansion differs. Okay, in the sense that these FABCs are different for E8 cross E8 and SO32. Okay. Now, what this means is the following. Okay. Given the existence of such operators, we can construct physical vortex operators, like the physical string states as follows. Let me write it. These are primary, I should have already said. Okay. So this you can easily convince yourself this is physical if physical if k square is 0 and k mu psi mu a equal to 0. Okay. So this basically tells us that there are massless gauge fields. Okay. So the 8 cross 8 heterotic string theory has gauge fields transforming in the 8 cross 8 representation. Sorry, the adjoint representation of 8 cross 8. And this one has gauge fields transforming in the adjoint representation of SO32. These are adjoint representation indices, right? A and B, because this comes in the structure constant. So physically, what this theory is described to heterotic string theory. Describes n equal to 1 supergravity in D equal to 10 coupled to 8 cross 8 or SO32 Young Mills, the super Young Mills. And of course, infinite tower of massive states. Now, the reason that this has n equal to 1 super symmetry is because you have only one set of gravity laws, right? Because there is only the NSR but no RNS, because on the left sector, the anti-holomorphic sector is bosonic string theory. Okay, so there is no distinction between NS and R. Okay. So we can discuss actually heterotic and type 2 string theory on the exactly in the same way. Okay. But what you're going to do from now on is that for simplicity, we'll focus on heterotic string theory. Okay. And essentially because this involves less writing. Okay. It has only two sectors. NS and R. Okay, this is characterized by right moving modes instead of 4. Okay. But whatever you are going to discuss will the generalization to 2B is to type 2 is straightforward. Okay, you can repeat whatever you are doing here for type 2 without much change.
I have a question.
Yes, go ahead, please.
Why are the currents primaries? Is it the same reason why the stress tensor is a primary?
No, it just so happens that in these CFTs, you find that the CFTs are fixed, right? Because as I said, the requirement of crossing symmetry and modular invariance fixes the CFTs. Okay. And you find that in that CFT, you do have dimension 1, 0 primaries with this property.
I see. Okay.
Is that clear?
Yeah,
see,
because...
Yeah, go ahead, please.
I just thought in Wesumanowitten CFTs, the currents are not primaries, so I was confused.
Oh, no, see, these are Virasoro primaries.
Oh, I see. Okay.
Not in Wesumanowitten, the currents are not primaries under the current algebra.
Yes, that's
but here you're talking about just Virasoro primary operators. I can write this down explicitly. These are Virasoro primaries, because that's what is relevant for the string theory analysis, right? The fact that they are secondaries of the current algebra doesn't really make any difference.
Yes, thank you.
Any other question? Okay, so now let me go back a little bit and consider the following problem, that instead of string theory, let us analyze the CFT a bit more. Okay, which means that you do, for now, you don't restrict yourself to the kind of additional conditions that we imposed. Okay, eventually, of course, for string theory, you have to impose those conditions, but let's just study the CFT a bit more. Okay, because it will give us some insight. Okay. So the question that we will study is that how to build states with picture number Q. Okay, that suppose you want to build all possible states with picture number Q, how do you go about doing that? So the way to do this, here at least one way to do this is the following. So you begin with a particular state of a given picture number Q, okay, which is e to the Q phi to the ik dot x acting on the vacuum. Okay, the whole thing evaluated at 0 acting on the vacuum. Okay. And then we apply the various modes of various fields, namely beta n, gamma n. We are doing heterotic. Okay. So that there is a beta bar, gamma bar, etc. Bn, Cn, B bar n, C bar n, and matter operators. And it's guaranteed that these will all give picture number Q state, because these are picture number singlet. Okay, they carry 0 picture number. Okay. So that's the way you build a full set of basis states of picture number Q. Okay. Now let's recall the definitions of beta n and gamma n, and those came from the mode expansion. And this minus 3 half basically reflects the fact that beta z has conformal at 3 half or 0 3/2, and the half reflects that gamma has conformal at 0 minus half. Now combine this with the following relation, that beta z e to the Q phi of 0 goes as z to the Q. Okay. Because beta z, let me remind you, had this del xi to the minus phi, right? So if you calculate the OP using the rules that I gave you, you can easily check that this goes as z to the Q. Okay. And gamma z e to the Q phi of 0 goes as z to the minus Q. Okay, because gamma has eta e to the phi. Okay, so that OP gives you z to the minus Q. So if you compare this, okay, we see that you get some condition on what kind of beta n can give you non-zero answer. Okay, because if, for example, this power becomes less than Q, okay, say Q minus 1, okay, then the corresponding beta n must annihilate this state, because if the leading term goes as z to the Q. So you cannot have any term for the form z to the Q minus 1. Okay. Similarly, here you cannot have any term of the form z to the minus Q minus 1. Okay. So just by comparing these two, you can check and again I'll leave it as an exercise, this is a simple counting, is that beta n on qk is 0 for n greater than or equal to minus q minus half, and gamma n on qk is 0 for n greater than or equal to q plus 3 half. Okay, so for example, let's suppose that n is equal to q plus 3 half. Okay, let's see what happens. If n is equal to q plus 3 half, okay, then this part here is z to the power minus q minus 3 half plus half. That's minus q minus 1. Okay, that's more singular than what is allowed. Okay, so the corresponding gamma n must annihilate this state. Is this logic clear? Okay, so let me write this again. Okay. So we get this relation that beta n on qk is 0 for n greater than or equal to minus q minus half, and gamma n on qk is 0 for n greater than or equal to q plus 3 half. Okay. And I should also just point out exercise that beta n, the n that in this expansion, n is integer plus half for q integer, and n is integer for q belongs to integer plus half. Okay. And that essentially follows because of this extra minus 3 half and half. Okay, so if n is integer, this expansion becomes integer plus half and vice versa. Okay, now using this, it follows that unless q takes one of these three values, minus half, minus 1, or minus 3 half, there is at least one positive n such that beta n on q k non-zero, or gamma n on q k non-zero. Okay, this is best checked by examining this formula carefully, but I'll just give an example. So example, suppose you take q equal to 0. Okay. Then this tells us that beta n on 0k is 0 for n greater than or equal to minus half, okay, and gamma n on 0k equal to 0 for n greater than or equal to 3 half. Okay. Now for q equal to 0, okay, it's integer, so n is integer plus half. Okay. So you see that gamma half on 0k is non-zero. Okay, some positive mode doesn't annihilate this. Now this is something that you are familiar with. For example, C1 acting on the vacuum is not 0. But here there is a difference because gamma is a bosonic oscillator. It's bosonic. Okay. So gamma half to arbitrary power on 0k is also not equal to 0. Okay. But what it does, the application of gamma half to the m, this one again, this I'll leave as an exercise. This one reduces L0 eigenvalue by m. Sorry, by half m. Okay. Each application of gamma half, okay, essentially takes L0 to L0 minus half. Okay. Of course, you cannot apply a single gamma half because that will destroy the GSO projection. Okay. But you can apply it in pairs. Okay. And if you apply m times, okay, you reduce the L0 eigenvalue by half m. Okay. So this essentially tells us that in such cases, the spectrum of L0 is unbounded from below. Okay. This is avoided only for the special cases. Okay, you can check that in these cases, okay, that is this problem doesn't exist. Okay. Q equal to -1 is the best case because there only the positive modes, only the negative modes give non-zero result. Okay. For Q equal to -3.5 and -3.5, there is still some issue in the sense that there is a zero mode, okay, which doesn't annihilate, either a beta zero mode or a gamma zero mode. So while you cannot reduce L0 eigenvalue, okay, at the same L0 eigenvalue, you can create infinite number of states. Okay. So it's a less serious problem, but it's still a problem. But all of these problems are resolved in string field theory. Okay. But this, let me just say at this stage itself that this is the reason, okay, why while deciding on as to which states are allowed string states, okay, allowed states of the string, we restrict to Q equal to -half and -1. Other questions? Okay. So now we are still in CFT, not quite in string theory at this stage. So let's consider the effect of plumbing fixture. So plumbing fixture is you just take WW prime equal to -q, right? Identify the local coordinates of two punctures by this relation. Okay. And as we have seen that this inserts, this is a general property of CFT, right? Whether it's bosonic or fermionic, it doesn't matter. Okay. It will insert the following in the correlation function. Okay. Now let's suppose that this one has picture number P. Okay. Let's suppose that this one has picture number P. Okay. So if this one has picture number P, this is the conjugate state. So this must have picture number -2 -P. Because you remember on a sphere, the 2-point function is non-zero if the picture number adds up to -2. Okay. So because this is a conjugate state, it better be that the sum of the two is -2 -P. Then we see that because this is an inner product, it's non-zero only if this one has picture number P. And if this one has picture number P, this one must have picture number -2 -P. Okay. So now let's consider two different cases. Okay. First one, when you show punctures on two different surfaces. Okay, it doesn't matter if it's a sphere or torus or anything. Okay, you can put some genus, doesn't matter. Okay. So let's suppose that we have sort them by this WW prime equal to minus Q relation. Okay. So in this case, okay, what you can say is that this has picture number P, this one has picture number -2 minus P. Okay. But in fact, we have no choice in this case as to what picture number state you should choose, okay, because the picture number of this is determined by the picture number of the rest. So picture number of this is determined by the rest of the vertex operator. And the genus. Okay, because on a genus G surface, the total picture number has to be 2G minus 2. Okay. So once you have put the picture numbers of this, you just add up everything and you find that you find whatever the picture number of this should be. Okay. So it's fixed. Okay, on both sides it's fixed, and it better be that they are related by this, otherwise the result will be 0. Okay. But the more interesting case is the one where you show two punctures on the same Riemann surface. So now suppose that we have show them. Okay. So now if this one has P, this one will have -2 minus P by this counting. But you see that the sum of the two is -2. Okay. So whatever P is, okay, these two always add up to -2. Okay. So this means that P is not determined by picture number conservation. So what should we do here? So the naive guess will be to sum over P. Okay, you have to have a completeness, so you have to sum over all possible picture numbers. In actual practice, we have to fix P. Okay. This is a peculiarity of this beta gamma CFT. Okay. And this has to do with the fact that in terms of beta gamma, we didn't have any picture number to begin with. Right? Beta and gamma have 0 picture number. Okay. Picture number entered the game because of the bosonization. Okay. If you had worked with beta gamma system, you would never have known about picture number. Okay. And somehow that essentially gets reflected in this. Okay. That to get the correct correlation function on this combined surface, okay, we have to sum over only a fixed P. Okay. Given this, we can ask which P. Okay. So what value of P should we choose? The answer turns out to be any one, any value. Okay. But this answer is a somewhat formal answer, and I'll explain why. Okay. Formally, you can choose any value of P and that will work. Okay. All P give the same answer. Okay, so you fix your P. Okay. Now, the reason that this is formal, okay, is because if you remember, okay, that we have unbounded spectrum. From below. Okay. So this Q to the HR, okay, Q bar doesn't matter. In heterotic string theory, Q bar makes no difference because the picture number, this problem appears on the holomorphic sector. Okay. So this Q to the HR, okay, this factor, this HR can become arbitrarily negative. Okay. So it's not clear what is the sum over R doing, right? Because Q is supposed to be a small number, and you are summing over this Q to the HS. Maybe I write it as HS, but it's the same as HR. So it can become arbitrarily negative. Okay. So it's not clear what we mean by sum over S. Okay. So the way one has to interpret it formally is by some kind of analytic continuation. Okay. So you have to make sense of this by analytic continuation. Okay. And that is if you have some sum like this, for example, okay, this sum makes no sense when Q is small. Okay. But nevertheless, we can formally sum it and write it as 1 over 1 minus Q inverse, okay, which is minus Q over 1 minus Q, okay, and make sense of this sum. Okay. So it's only by thinking of this sum over S formally that you can make sense of what this answer is. Okay. But once you adopt that convention, okay, we can show that the NEP gives the same answer. Okay. And clearly in this case, P equal to minus 1 does not have this problem. There the formal sum is actually a convergent sum. Okay. P equal to minus half and minus 3 half have mild problems. Due to essentially either beta 0 or gamma 0 doesn't annihilate the vacuum. Okay. But this is cleverly taken care of by in string theory, and we'll see. In string theory. Okay, and we'll see how this is done. So far, basically we have analyzed CFT correlation functions. Okay. But this already gives you a motivation as to why P equal to minus 1 and P equal to minus half are spatial. Okay, from this perspective, minus half and minus 3 half are both spatial. Okay, but at least you can get some idea of why we want to restrict string fields to be within this class. Other questions? Okay, now let me make another point about homogeneous amplitudes. High loop amplitudes. And that is that we have to sum over spin structure. And this means that we have to sum over periodic and anti-periodic boundary condition. On beta, gamma, psi, mu, along different cycles, different non-contractible cycles. So if you are having a torus, for example, then it has two independent non-contractible cycles. Okay, so let me draw this. So one is here, okay, and the other one is this one. Okay. So on this beta gamma psi mu, you put periodic boundary condition and anti-periodic boundary condition along these cycles, and also periodic and anti-periodic boundary condition along this cycle. And the physical reason for this can be understood from using again the plumbing fixture picture. So imagine that we have constructed this torus by taking a sphere with say 3 punctures and then showing 2 of the punctures to each other. In this showing, this could be either NS or R. If this is NS, this also has to be NS. If this is R, this has to be R, right? Because otherwise the inner product just vanishes. Okay. So this can be either NS or R. Okay. And this means that this corresponds to anti-periodic or periodic boundary condition along the mod W equal to mod Q to the half circle. Okay, and that of course becomes one of the non-contractible cycles on the torus. Okay. And similar justification can be given for this. Okay. So the fact that you have to sum over spin structure is not unrelated to the fact that you have both Ramond and Nebel-Schwarz states. Okay. The fact that in a propagator you can have both Ramond sector propagating and Nebel-Schwarz sector propagating, okay, reflects itself, okay, in the fact that you have to sum over all possible boundary conditions. Is this clear? So in the following, I am not going to write down the sum over spin structure explicitly, okay, but let me just say where it will be encoded. Okay. So we'll define MGMN as the modular space of Riemann surface of genus G with MNS and N Ramond puncture. Now, if you are dealing with type 2, then you have to have 4 levels, right? Because there are NS, NS, NSR, RNS, and RR, right? So that's why heterotic it's just simpler to write this. Okay. Now, locally, this MGMN really is MG and M plus N, right? It doesn't matter whether a given puncture is Ramond or Nebel-Schwarz. Okay. But globally, it turns out that there is some subtle difference. So I write this MGMN. Okay. And then when I write something like integral over MGMN, okay, this will include sum over spin structure. So I'm not going to write down separately the sum over spin structure in the various formulae that I'm going to write down. Are there questions? Okay, so now let me start with let me go to string amplitudes. So for this, we need to integrate something. Over this modular space. But what is this something? Okay, that's what we are after. Now it turns out that we can take two possible approaches. Okay, so let me just write down what those are, and then I'll focus on one of them. So the first one is to make worldsheet supersymmetry as manifest as possible. And this leads to a formalism which is called the supermodular space. So what is supermodular space? Here, what happens is that besides the usual bosonic coordinates, of MGMN, we have a set of Grassmann odd variables. Okay. So these are what are called the supermoduli. Okay. And the number depends on G, M, and N. Okay, we'll see this number indirectly later. Okay. So here is you see the difference between Ramon and Neveu-Schwarz punctures. Okay, they depend separately on M and N, but not just on M plus N. Okay. So the idea is that you try to formulate this as a integral over both bosonic variables as well as the harmonic variables. Okay, and try to construct the integral. Okay. This certainly is more geometric, but this has not been developed to the extent that the other one has been developed. So I'm going to describe the other one. Okay. Now, in principle, the other one can be related to this. Okay, although it has never been achieved from first principle, but let me just say what the formal relation is. So the second approach is that we just carry out the integration over the Grassmann odd moduli explicitly. Okay. So this can be done locally in patches of MGML. Okay. And essentially what it does, okay, it essentially leads to insertion of picture changing operators on the worldsheet, on the Riemann surface. So which you can write as product over alpha chi of y alpha. Okay, y alpha are the locations of the picture changing operators. Okay, the number of alphas. So alpha runs from 1 to the number of picture changing operators is, okay, we can figure out how many number of picture changing operators are. Okay, so let's say k. So to figure out what the value of k should be, okay, we have to use a picture number conservation. Okay, so the k picture changing operators will have a picture number k, each has picture number 1. Then we have m Nebel-Schwarz vortices. Okay, so m times -1 plus n times -half. So this should be equal to 2g minus 2. Okay. This means that k, the number of PCOs, so let's say alpha equal to 1 to k, should be equal to 2g minus 2 plus m plus n by 2. Okay. And these are the number of odd moduli. Number of odd supermoduli, where each supermoduli integral is supposed to bring down one PCO. Is this clear? Okay. Now I have not told you what these y alphas are, right? These are some points on the Riemann surface. Okay. So it turns out that the choice of y alpha corresponds to choice of some gauge. Okay. And this gauge choice breaks down. Okay, and that's why we'll see this. This we'll probably see in the next lecture, that we have to keep changing the positions of y alphas. Okay, we cannot just take the same y alphas everywhere on the Riemann surface. Okay, other questions? Okay, so now we are going to construct the amplitude. Okay. So to do that, we have to find the analog of this omega that we had introduced. And this will be a function of all the states. So V1 to Vm, these are the Nebel-Schwarz vortex operators. And let's call them W1 to Wn. These are the Raman sector vortex operators. Okay, so this should be a P form. Okay, in an appropriate version of this PGMN that I introduced. Okay. And you have to find what this is. You have to construct this. Okay, and the guideline for constructing this will be again various consistency conditions. So let's proceed. So first step, as in bosonic string theory, we introduce m plus n disks dA with coordinate WA. Then 2g minus 2 plus m plus n spheres SI with coordinate ZI. And 3g minus 3 plus 2 times m plus n circles CS, which basically give the interface of the boundaries between Si and dA or between Si and Sj. And we have some transition function, which is sigma s equal to Fs of tau s. So this is the same as in bosonic string theory. Okay. The extra ingredient we have to specify locations y alpha of 2g minus 2 plus m plus n by 2 PCOs. Okay. These could be either on the disks or on the spheres. Okay. But we'll use the convention, okay, that we take this to be in WA coordinate if on dA, okay, and in ZI coordinate if on SI. Which means that if I talk about y alpha, okay, if the alpha punctured is on the disk dA, the y alpha is the coordinate in WA coordinate system. Okay. If the alpha puncture is on SI, then y alpha is a coordinate in the ZI coordinate system. Okay. It's natural, but that's what you have to choose. Are there questions so far? Okay, then third step is to introduce the fiber bundle EGMN. So here there is a difference. So this is MGMN as usual. Okay. So this includes spin structure information. Okay. Here earlier there is local coordinate information. At punctures. The additional information that we will include here is the PCO locations. Okay. So these will be part of the fiber coordinate. Okay. So let's suppose that TM is a coordinate on PGMN. Okay, of course, it's infinite dimensional. Okay, so this is infinite dimensional coordinate system. Okay. Then this means that we have sigma s, this function, okay, will now depend on t, because different t will correspond to different functions. Okay. And the y alphas will also depend on t. Right? Because different t will correspond to different choice of y alpha typically. Okay. So either this differs or this differs, or even maybe both differ when you change t. So now you have to define the analog of BM. Okay. So part of it will be this identical to what we had for the bosonic string. So let me write it. So this bar is only over the numerator. The numerator is still TM. Okay. Xi is that fermion field that we got from the by bosonizing the beta gamma. Okay. So remember that beta gamma got traded in by xi eta phi. This is that xi. Okay. So this is the extra term. This is the extra term. Now the peculiar property of this extra term seems to be this 1 over chi, right? What when we have not defined 1 over chi. Chi is just a local operator, right? So 1 over chi doesn't make sense. Okay. So this is formal. We'll see that this basically will go away. Okay, it will cancel against something else. So this is just formal. Write it for now. Just accept that this is written formally. Okay, we'll see after you put it inside a correlation function. If there is a 1 over chi left over, then you are in trouble. Are there questions? Okay, so now let me write down the formula for omega. Maybe I use a different color. So this is the P form on omega on PGMN that we construct. Now you see that here you have this product over all the picture changing operators. Okay. So what happens is that if when you put in this BM1 to BMP, okay, then these things you can first of all convince yourself that this can appear for a given alpha. This chi y alpha can appear at most once. Okay, because this will be antisymmetric when you put two of them together. Okay, and will vanish. So that because it appears at most once, okay, it will get cancelled by the corresponding chi factor here. So that's the way we should interpret this formula. Okay. So this, once we expand this out, this is a completely well-defined formula. Are there questions? Now this looks like a complicated formula, right? So how did we arrive at this? And the short answer is that this one satisfies the identity that was so important for us. Okay, so these terms basically correspond to QB acting in turn, and with this -1 to the V factors picked up, this is -1 to the P d omega and as you know that this identity is essential to show the section independence. Okay, so now the amplitude I can now write down. So A V1 to Vn, Vm W1 to Wn will be this GS factor. Oh, I should have also written some minus 2 pi I factors. Okay, so let me write it here. It's times minus 2 pi I times minus 3g minus 3 plus m plus n. Okay, the same kind of factor that we had in the case of bosonic string theory. Okay. So here you have also this gs factor, gs to the power 3g minus 3 plus m plus n. And then integral over s gmn of omega gmn 3g 6g minus 6 So this is exactly the same structure as in the case of bosonic string theory. And as I said, once you write this, then it has all the nice properties. So this is a section of PGMN, which means it basically can be written as an integral over MGMN by pulling back. And the point is that once you have written it this way, okay, then as a consequence of this, you can show first of all that it's independent of the section, the pure gauge states decouple and so on. Okay, all those proofs go through exactly as before. Is this clear? Are there questions? So once we have gotten this, we can now express the amplitude as sum over Feynman diagrams. The procedure is the same as in bosonic string theory. But with one difference. And I'll explain this and then I'm going to stop. Now, I should have also said that this prescription in principle, one should be able to derive by starting from the supermodular integral, okay, and then doing the Grassmann odd integral or integration over the Grassmann odd variables explicitly. Okay. But this has not been shown from first principle. I should say certainly we have some idea, right? It does work to some extent, okay, but the full procedure has not been established from first principles. Okay, so let me explain what is the difference. So consider this plumbing fixture. And this inserts. Now we are doing also the integrals. Okay, so this will insert integral dq h dq bar, and then phi rc b0 bar phi sc q to the hs q bar to the hs bar. Okay, this is the same as in what we had in bosonic string theory. This is phi r and phi s. Okay, so you interpret this as a propagator joining two vortices coming out of Feynman diagram. Now, if these are NS punctures, so for NS punctures, phi r and phi s have picture number equal to -1. So this implies that phi r c and phi s c have picture number -1, and everything is fine. So this is perfectly okay because this is non-zero. Now let's look at the Raman puncture. So here, phi r and phi s have p equal to -12. Why? Because now that we are doing string field theory, or we are doing string theory, okay, we have already declared that the states of string theory are picture number -12 states in the CFT. Okay. So you have no option but to change, pick phi r and phi s to have p equal to -12. But now you see there is a problem because this implies that phi r c and phi s c have p equal to -3/2. So we don't get picture number conservation. If this is -3/2 and this is -3/2, the total is -3. So this means that that this matrix element phi r c b0 b0 bar phi s c will vanish. So to avoid this, okay, we avoid this. By inserting one picture changing operator, one PCO inside this matrix element. Okay, in what form we insert it, I'm going to describe in the next slide. But is this procedure clear? Because then -3/2 plus -3/2 plus 1 will add up to -2, which is the correct number. Okay. So what we insert a particular combination of the PCO, chi0, which is integral dw by w by w. So this means that this is like an average of PCO insertions on a circle. Okay. So roughly what it means is the following. Okay. So I said that to pick SGMN, okay, we specify this. I mean, let's look at this picture. So if you take PGMN, okay, then specifying a section, okay, means that you are specifying both the local coordinates as well as the PCO locations as a function of MGM. Now, what this is saying is the near degeneration, okay, when Q is small. So this specifies local coordinates and PCO locations. Now, what this condition tells us is that the section that you choose, okay, has to have some special property near the boundary. Okay. Namely, that if the two Raman punctures which are being sought, okay, if that is the kind of boundary that you are considering, okay, then one of the PCOs must be inserted on the neck. One of the PCOs must be inserted on the neck, okay, where you are sewing them together. Furthermore, it has to be inserted not as a single object, okay, but as an average of many insertions. Okay. So one PCO insertion is average of all possible insertions on mod W equal to Q to the half circle. Okay. So next time we'll see some example of this, okay, and maybe that will make things a little more clearer. But I think today my time is already up, so I'll stop here and ask for questions.
So are there questions? There are questions?
Well, I wanted to ask whether it is possible to make a different choice of central chart when talking about.
Sorry, I think your voice is getting cut. Can you?
Yeah, you have to use what is the other one.
I wanted to ask, when you talked about heterotic string theory, you assume that we take 10 bosons and then we add a CFT having a central charge 16 and 0. I wondered if it's possible to make a different choice and still have a theory, a CFT that makes sense.
The point is you need this QB square equal to 0 condition, right? So if you don't have the beta gamma ghost, okay, the central charge has to add up to 26. Otherwise, you will violate the QB square equal to 0 condition. So
wouldn't it be possible to, let's say, take a central charge of 10 and then take 16 free bosons?
Then on the supersymmetric side, you have problem, right? The central charge will not match up to 0 in that case. Because on the supersymmetric side, you have beta gamma ghost. Okay. And the beta gamma ghost, as we have seen, gives the total central charge of 11, right? And the psi mu gives d by 2. So that on the holomorphic side, if you want the total central charge to vanish, you cannot have 16 x mu's.
Okay, I see. Thank you.
Other questions? People online? So I have a question. So this choice of inserting X naught on the neck when you glue two Ramon punctures, how much is it really obliged choice, or is it just an easy choice?
Well, actually, it is more or less obliged into closed string theory, because what you need is that it should commute with this B0 bar operator.
Oh, I see.
And that essentially fixes this choice. Okay, if you take, for example, a chi at a single point inside this, it will not commute with B0 bar.
I see. So this is like a Siegel gauge in the string field theory language somehow.
Yeah, so here, of course, we are working in Siegel gauge, but even in the gauge invariant form, right, the condition is that it should commute with B0 minus. And that forces you to have this particular structure.
Mm-hmm. So even if you would construct this from string field theory and use another gauge fixing that is not Siegel gauge to define the propagator and do the plumbing fixture with this propagator, then you would still have to use X naught, or would you have to use?
Yeah, you have to still use X naught. Because basically to prove gauge, if you start with the gauge invariant version of string field theory, then to prove gauge invariance, you need this X naught. Because you need the fact that B0 minus has to commute with it, whatever you insert.
Oh, okay, I see, okay.
Yeah, otherwise you break gauge invariance.
Okay.
I have a question.
Yes.
So there are no tachyons in the heterotic string theory, even though there's a bosonic sector.
That's right, yes. Because we have this L0 minus equal to 0 condition, right? L0 equal to L0 bar. And using that, one can show that basically the having one supersymmetric site removes the tachyon.
Oh, I see. Okay.
So I remind that there is not going to be the question and answer time this afternoon. So if you have questions, this is the moment.
Yeah, I have one more. Maybe, yeah, okay. When we're talking about modular space, we say that it has some finite dimensions, but what are the parameters that we can use as coordinates on this, or can we think even of coordinates?
So locally, it is reasonably well understood. Basically, if you think of, maybe I draw one figure. We had this this is G equal to 2, N equal to 2, but the general picture is still valid. So we had this so we had, remember, we had 3G minus 3 plus, well, I can call it M or M plus N circles, right? CS. So on that circle, we wrote down a general relation as sigma is equal to Fs of tau s. But of course, there is a lot of redundancy, because you can change coordinates. You can make a reparameters of the z's and the w's if you are not interested in local coordinate. Okay. So locally, at least, you can parameterize a modular space by taking sigma s equal to minus qs over tau s. Okay. Basically, the plumbing fixture kind of variable. Okay. So this gives you altogether 3g minus 3 plus m plus n qs. Okay. So this means 6g minus 6 plus 2m plus n real parameters. Okay. And this you can use to label the modular space. The non-trivial part, which requires some understanding. In fact, I mean, there is no really efficient way to do this. Okay, is to see what is the range. Okay, what you should integrate over, so that you don't overcount. Right? Because you know that Riemann surfaces have these global symmetries. Okay, for example, if you have a torus, you can exchange the two cycles. Okay, and that doesn't give a new torus. Okay. So there are a lot of identifications under these global symmetries, and to understand exactly what range of these parameters give inequivalent Riemann surfaces, that's a much more complicated problem. But locally, if you want to know what coordinates you want to use to label the modular space, you can just use this.
But can there be a situation when, for example, one of the coordinates some kind of winds on the circle, and another, yeah, also do some non-trivial, yeah, behavior.
Yeah, so you can in fact use okay, let me.
Yeah, because this form looks really constrained, and it is, yeah, just not really.
Oh, so there's certainly a lot of freedom, right? Because a lot of the freedom is in the change of coordinate system, right? I've just given you one. Okay? But you could, for example, use this. You could use this, okay, on when you have the intersection of two spheres, okay? And then something like sigma s equal to tau s plus as on SI intersection dl. Okay. Again, as is two complex parameter or two real parameter. Okay. So as far as parameter counting is concerned, it gives us exactly the same set of variables. Right? So there is a lot of freedom in labeling the moduli space. Okay. You basically need these many parameters, right? And unless you are unlucky that you have chosen the parameters in such a way that varying the parameters actually can be removed by coordinate redefinition, any choice of any parameterization of this kind is good enough as far as local region is concerned. So it's by no means this is a unique choice. Does this answer your question?
Yeah, I guess. In some sense, yeah. Maybe I just need to think of it a little bit more. Yeah. Okay, thank you.
Yeah, so it's basically that you want to introduce these many parameters and you can do it in many different ways, right? Through these functions.